Hello everybody, welcome to my YouTube channel again. My name is Thomas and today we'll be going through the expressions for velocity and acceleration under the polar coordinate system. Alright, let's get straight to it. So normally when we express velocity and acceleration, we use the xy coordinate system. Suppose this is our xy plane and our particle follows this path. Then we have the position vector, our arrow. The position vector has two components, x of t and y of t. Then velocity, which is defined as the derivative of r, equals this. And then acceleration, which is the derivative of v, equals this. But okay, this is just the expressions under the xy coordinate system. We want to derive the alternate expressions in the polar coordinate system. Now, in the polar coordinate system, we don't have x and y anymore. Instead, we have r hat and zeta hat. R hat is the unit position vector. It's basically the position vector, but we force it to be a unit vector. We denote the unit position vector by r hat. And we also have another unit vector called zeta hat, which is defined as the vector that is perpendicular to r hat. And without loss of generality, we assume that zeta hat is in the counterclockwise direction. It doesn't matter as long as you fix the direction, because we just need things to be consistent. Alright, now under this polar coordinate system, the position vector is now expressed as r times r hat. And r without the arrow just represents the magnitude of the vector, of the position vector. Okay, so velocity is still defined as the derivative of r arrow. And this time, using the product rule, we can expand to get dr dt r hat plus r dr hat dt. And in case some of you are wondering why the product rule applies to a scalar multiplied by a vector, then if you need, I can create another video and cover it for you. But yes, for now you just need to know that the product rule does apply to a function which is the product of a scalar function and a vector function. Okay, actually dr hat and dt can be simplified into more basic elements. And in fact, we'll derive the expansion of dr hat dt. Suppose our position vector initially was r1 hat. It changed after an increment in time of delta t to r2 hat. Okay? This is part of a circle that it covers. Then this part would be delta r hat, which is the increment in the unit position vector. Now, the magnitude of this would be equal to the magnitude of this over delta t. No, approximately equal. And then this is approximately equal to, since r hat is a unit vector, it has a magnitude of 1. So this thing approximately equals delta zeta. Alright, delta zeta is the angle. Delta zeta over delta t. And as delta t approaches 0, we get this. Oh no, sorry. d zeta dt, and some would recognize this as angular velocity. Alright, so now we have the magnitude of dr hat dt. Actually, it's very intuitive that the direction of dr dt is zeta hat because the velocity is tangential. But if you need a rigorous argument, then I can provide you with one. Since r hat is a unit vector, its magnitude is always equal to 1. So r dot r is always equal to 1. Now, differentiating both sides, we get r hat dot dr hat dt plus dr hat dt dot r hat equals 0, which is 2 times r hat dot d r hat dt equals 0, which is r hat dot d r hat dt equals 0. And this says that dr hat dt is in fact perpendicular to r hat. And that means that it has the same direction as theta hat. Okay, so now that we know the magnitude and direction of the vector, we can express it. So dr hat dt equals, in this case, no, since we're assuming that r hat is moving in a clockwise direction, I'm just going to assume that theta hat is not in the counterclockwise direction, but instead in the clockwise direction to make things simpler. Now, so dr dt equals, well, the magnitude of dr dt was d theta dt. The direction was theta hat. Yes, dr dt equals this. And then substituting this into this equation, we get v equals dr dt r hat plus r dr hat dt, which equals dr dt r hat plus r times, d theta dt theta hat. And this is velocity. Now we only need to derive acceleration. And to derive acceleration, we just have to differentiate v with respect to time. Alright, so a equals dv dt equals, well, let's just do the code hard calculations. First, I'm going to copy this thing down here. It equals d square r dt square r hat plus dr dt dr hat dt plus dr dt d theta dt theta hat plus r this thing, and then a final right? Okay, so first of all, we notice that there is something new, and the new thing is, in fact, d theta hat dt. So before we move on, first we need to expand d theta dt and represent d theta dt in terms of r hat and theta hat. Okay. So our initial position vector, unit position vector, was r1 hat, and at that time, theta 1 hat was this. But after an increment of delta t in time, r1 hat has changed into r2 hat, and theta hat has become theta 2 hat. And again, this angle is delta theta. So just pulling out theta 1 hat and theta 2 hat, one can see very easily that the angle between theta 1 hat and theta 2 hat is in fact delta theta. And I could prove this, but it's a non-trivial geometric proof, so do it yourselves. And the angle between theta 1 hat and theta 2 hat is delta theta. So by a similar argument, this thing would be delta theta hat. Delta theta hat. Okay, now the magnitude of d theta dt equals delta theta hat's magnitude over delta t. And using a similar argument to the one we used last time when we derived dr hat dt, this thing, this is approximately equal. And then this thing approximately equals delta theta delta t. And as delta t approaches 0, we get d theta hat dt exactly equals d theta dt. Amazing, right? As you can see, as delta theta is smaller and smaller, these angles get bigger and bigger. And when delta theta equals 0, these two angles are in fact 90 degrees. And this means that the direction of d theta dt points towards the center. So in fact, it has a direction of negative r hat. Therefore, we say d theta hat dt equals d theta dt times negative r hat. Okay, now we are going to substitute all of this in to A's expression to derive a somewhat beautiful result. Okay, let me just copy this thing. Nah, wrong thing. Wrong thing. Sorry for the inconveniences. Trying my best. Copy this. Paste it here. Yes. And then don't forget this is A. A equals this. Alright. D square R dt square r hat. This is already in its most simplified version. No need to touch that. Dr dt. Expanding dr hat dt, we get d theta dt theta hat plus dr dt d theta dt theta hat. This is also something that doesn't need to be further simplified. And then r, the second derivative of theta hat. We don't need to touch that. And then this one, d theta dt negative r hat. I'm correct, right? It was negative r hat. Yes. And then combining like terms, we get, putting all the r hats together, you see, this one has an r hat. And this one has an r hat. So, d square r dt square minus r d square theta, d theta dt square. And then putting all the theta hats together, we get 2 times dr dt d theta dt, because these are the ones with theta, and then plus r d square theta dt square. Alright, but there's a clever trick that can be applied to this place in order to further simplify. And notice that d dt r square d theta dt, there's parentheses here, this thing equals 2r dr dt d theta dt. By the way, this is by chain rule, plus r square d square theta dt square. And comparing these two expressions, we see that the only thing that is missing is a power of r. So in fact, we can further manipulate this expression into the form. Wait a second, just let me finish writing it. We're gonna multiply 1 over r here so that the buddies inside can be up in r. And voila, we have the final result. Oh god, my writing is so slow. D dt r square d theta dt. Yes. And this is the final expression of acceleration in the polar coordinate system. In fact, these formulas are very, very useful. From now on, we don't have to be restricted to the XY coordinate system, and instead we can change freely between these two coordinate systems. Later on, you will meet a lot of other coordinate systems. And let this be a very useful thing that you have hopefully learned. Goodbye.